All right, so we're going to continue our discussion with capillaries. So here, remember that capillaries connect arterioles, which are the smallest arteries, to venules, which are the smallest veins. Capillaries themselves are usually only about 1 millimeter long and 8 to 10 micrometers wide, 8 to 10 1,000th of a millimeter wide. So they're about the size of a red blood cell. Here's an electron micrograph of a red blood cell. Obviously this is colored, going through a capillary here, okay? So erythrocytes, the red blood cells, have to go through one at a time. And that means that the most surface area possible of the red blood cell hits the wall of the capillary to enable gas diffusion. So you can see that's really, really narrow and makes for very efficient gas diffusion, both in the lungs and at the tissues. So remember, capillaries only have a basement membrane and the endothelium. Okay, they don't have any other tissues or layers or anything. So the gases and nutrients diffuse very easily. So this is gas exchange at an alveolus, which are the air pockets in the lungs. So the air coming in is high in oxygen, and the blood coming in through the capillaries has already been to body tissues. It's already been through this systemic circulation, so it's high in CO2, shown here in blue. So as these blood cells come by, oxygen is able to diffuse into them because there's more oxygen inside the alveolus than there is in these red blood cells. Carbon dioxide diffuses the other way because there's more carbon dioxide in the cells than in the alveolus. And so as they move through this capillary that wraps around the alveolus, the oxygen diffuses in, the carbon dioxide diffuses out. Then when we get to tissues, we're going to have the same kind of mechanism, but in reverse. CO2 is going to diffuse into the bloodstream. Oxygen is going to diffuse out. So oxygen is going to go to tissues where they are low in oxygen. CO2 is going to go into the bloodstream when the tissues are high in CO2. So this is a capillary bed with an arteriole and a venule. So the blood's coming in this way through the arteriole. It can then branch off through this meta-arteriole. So we actually, instead of having a direct capillary coming off of the arteriole, we actually have this little meta-arteriole. And remember, meta means next to. So this is a little arteriole next to an arteriole. And it's going to flow all the way across this capillary bed to the venule. This is a really important mechanism for two reasons. One is that you remember from our blood lecture, you remember that white blood cells are larger than red blood cells. And if the capillaries are one red blood cell wide, then the white blood cells literally can't go through there. So the white blood cells go through this meta-arteriole. Okay, it's providing a thoroughfare so that they can pass through to get to the venule, to continue on through the circulation. Now, the other thing that's happening here are these little circles of smooth muscle, which are the precapillary sphincters. In this diagram, the precapillary sphincters are relaxed, and so blood can freely flow from the arteriole to the meta-arteriole and into the capillaries. If the precapillary sphincters are closed, if they contract, then that cuts off blood supply to the capillary bed. If you do that, then there's no way for the blood to get from the arteriole to the venule. So by having this meta-arteriole, the blood can go across. Now, these precapillary sphincters can cut off blood flow to capillary beds when it's not needed. And they're constantly cycling on and off in different tissues to supply blood to tissues when they need it and to shunt blood away from those tissues when the tissues don't need it. So, for example, while you're digesting blood, or excuse me, while you're digesting food, I hope you're not eating blood. While you're digesting food, you're going to need more blood flow to your digestive system. And so the precapillary sphincters around your digestive system are going to be open so that all of those capillaries can get lots of blood flow through them to get all those nutrients that are being absorbed in your digestive system. When you are cold, on the other hand, the surface capillary beds under your skin are actually going to close off so that you reduce the amount of heat that you lose to the environment by this blood flow directly under the surface. So, and they're not like turning off and then staying off in most cases. That can cause tissue damage. That's actually what happens if you get frostbite. What's normally happening is they'll turn off for a little bit and then cycle back on and then turn off and back on. So there's less blood flow, but not no blood flow to the tissues. And you remember the capillary sphincter? See, he's a little circle of muscle, of smooth muscle. There he is, a little circle of muscle, right? Okay, go back to the eye lecture if you don't remember that cartoon. Okay, now there are 3 types of capillaries. The main, most common type of capillary is what we call a continuous capillary, meaning that the wall of the capillary is continuous. All the epithelial cells are connected to each other, and in order for something to go from the lumen of the capillary to the tissues outside, it has to go through these cells. Some materials pass through by diffusion, some by pinocytosis. You remember that's the movement of fluid through into a cell by vesicle. And so that's what all these little things are. These are vesicles doing pinocytosis. And these are found all over your body, in your muscle, in your skin, in your lungs, not your digestive system. But most of your organs are going to have continuous capillaries. Now, fenestrated capillaries have little pores or fenestrations in the walls of the epithelial cells. And these are little passageways, little canals that go straight through so that fluid can much more easily exit from the lumen out to the tissues. So we see lots of these in the small intestine where fluid's actually going into the capillaries because we want to get as much water and nutrients into the bloodstream as possible. That's what your digestive system is for, after all. A lot of your endocrine glands have these because hormones are released often as big protein molecules. They can flow into the bloodstream very easily through these pores. And the kidney is going to have fenestrated capillaries to enable lots of fluid to get out of the bloodstream so that waste can be filtered out of that fluid and then removed from the body. Okay, so those are fenestrated capillaries. How are you going to remember this word fenestrated? You are going to remember this word, defenestration, which is one of my favorite words in the English language. It literally means to throw something out a window. Window in Latin is fenestra. So here is a computer, an old school computer monitor being defenestrated. You see, thrown out a window. If you throw a computer monitor out, that is a defenestration of a computer monitor. If you throw your political opponents out, that's what happened during the defenestration of Prague in 1618 when a group of city leaders were thrown out the windows because a bunch of people didn't like what they were doing. Pro tip, if you're going to throw your political opponents out the window, make sure that there is not a giant pile of horse dung underneath that they land softly on, come back up really pissed off at you. That's what happened in the defenestration of Prague. So there you go. Defenestration, defenestra, out the window. To help you remember, fenestrated capillaries have little windows, little holes in their walls. Okay, so that's the second type. We have continue, we have fenestrated, and then finally we have sinusoids. So you remember that a sinus is a cavity, right? We had sinuses in the skull. Those are cavities in the skull. Sinusoids are sort of cavities. They are also called discontinuous capillaries because the walls literally aren't connected. They have these huge holes in them, and there are holes in the basement membrane as well. This seems weird, right? So like it seems like the blood's going to flow through here and just everything's going to flow out the sides, including the red blood cells, and that's exactly what these sinusoids are for. The sinusoids themselves are often larger than other capillaries. This is going to allow for big proteins to very easily get in and out, but also allow red blood cells to flow out of these capillaries, which is why we see these in the bone marrow, where we need blood cells to flow into the capillaries, in the spleen and the liver, both of which you remember from the blood lecture. The spleen and the liver both monitor red blood cells for their health. Well, they can't do that if the red blood cells remain inside capillaries. The red blood cells have to get out of the capillaries. So the red blood cells flow out of the capillaries and are examined by cells within the spleen and the liver and then flow back in if they're healthy. Okay, so that's sinusoid. So three types: continuous, fenestrated, which has pores, and sinusoids, which has big holes in the wall. Okay, continuous, found in muscles and skin. Fenestrated, found in the digestive system, kidneys. Sinusoids, found in the spleen, the liver, and the bone marrow. All right, so we did the arteries and the capillaries. Now it's time to learn about the different types of veins. I'm going to come back to that in a third section.